Hello, I am Patricio Rodriguez, professor of the Center for Advanced Research in Education from the University of Chile. I am the director of this joint project between the University of Chile and Adolfo Ibáñez, funded by the Chilean National Science and Technology Foundation. The purpose of this talk is present to you how data analytics can support both the decision and policy making process in the educational system. Chile is in the middle of an educational reform. One of the main challenges is returning the administration of the public schools to the central government, because since 1981, the management of those schools became responsibility of the local governments or municipalities. Chile is a very diverse country, with almost 18 million people mainly concentrated in 10 cities and extreme climate conditions from a desert at the north to glacier fjords at the south, and a highly stratified society with a Gini index of 0.51. But our educational system doesn't function in the void. All these differences push and constrain the decision that families take in our supposedly free education market. So the question is how can we make explicit those invisible relationships to incorporate them in the actual decision and policy making processes? Using data science techniques, we developed several explanatory and predictive models using Microsoft Azure Cloud Computer Services. In this section, we will discuss three examples. First of all, we visualize the data from the enrollment of primary and secondary students. With the information of the municipality where the children lives and the school where they study, we create a map showing the daily displacement of students, where the width of each line represents the quantity of the student moving. If we filter the fluxes belonging to each origin and destiny, we can easily identify patterns where some municipality import a lot of students. For instance, at the center of the map, we see green lines converging to the municipality of Santiago. Additionally, if we continue filtering the lines, we can see that there are fluxes even greater than 10,000 students from Puente Alta to La Florida. This has a lot of collateral consequences as air pollution, traffic congestion, time and opportunity costs in subsiding public transportation. So, how we can explain why did the student move so much in Santiago? We will examine the current coverage of enrollment for all education considering urban accessibility. To explain this model, I will introduce first a few concepts. The first one is urban accessibility. The possibility that people have to move in the city are constrained by the geometry of the city, the transportation mode that individuals use, and the quantity of users at a given time. To model that, urban planning introduced the concept of isochron, which defines an area in a map which is reachable from a given location using a specific transportation mode in a given time. For instance, a 10-minute walking distance. Therefore, the isochron from a location acting as a supply node, for example a school, is shown as the orange amoeba in the figure. With this area, we find also demand nodes which ask for the services in the supply nodes, for instance the student population in each block. Therefore, using the ratio between the capacity of the offer node, the vacancies in the schools, and the total demand with the isochrons, can we create an index for the service given for the supply node, K, S sub K, and have a measure of the coverage of the specific service in the city, in this case providing education. After that, we can calculate the level of service for each block K in the city, or V sub K. To calculate an school service index, we calculate the ratio between supply and demand of schools within a 10-minute walking distance from each block in Santiago de Chile, using the 2002 census, the more updated data at the time of the analysis, and the enrollment statistics of 2012 from the Ministry of Education. The results are shown in the following maps. The most remarkable finding is that there are gray areas in the map showing a zero level of coverage. That means that every gray block doesn't have a school within a 10-minute walking distance. Using this model, we find that more than 400,000 students have not a school close to their block, and therefore they have the need to move far from the neighborhood they live to go to the school. Additionally, this has a clear implication for other ministries such as transportation and health, which deal with the consequence of these trips, which is around 40% of the total daily displacements. And there is a reason, that's because students move every day. Also, the map shows that the coverage of education in the city is very heterogeneous. There are a lot of municipalities that are very below the city average of 0.82, such as Huechuraba, Lo Barnechea, Lo Espejo, and even Puente Alto. If we superpose the daily displacement fluxes, this time coloring the lines using the municipalities which exports students, we can see that displacement went to the closest municipality with better service indexes, explaining, for instance, the 10,000 student displacement from Puente Alto to La Florida. Making visible this difference in school coverage across the city pushes two decisions. First, to define a minimum standard of coverage for all the municipalities in the city, or for each municipality individually, and second, providing a plan to bridge the divide between the current coverage and the desired standard. The previous model supposed that all the students have the same likelihood of displacement, but we know that the socioeconomic status of the students constrain their expenditure in transportation. Therefore, not all the students have the same opportunities to access to proficient schools, which condemn them to a vicious cycle of school failure. Thus, there are a geography of educational opportunities, that is, how the inequity in access to quality education spreads around a territory. To model that, we create a service index which corrects the demand calculation, weighting the population for this probability of displacement given their socioeconomic status. The probability of each socioeconomic status was calculated using a sample of geographically allocated students, attributing them the socioeconomic status of the block they live, and calculating the distance to the current school using a transportation model. After that, a probability distribution was adjusted using standard statistical methods. In the supply side, we only consider the capacity of proficient schools. We define proficient schools as the one where at least the 30% of its students achieve an adequate proficiency level in both national standardized tests of language and mathematics at 4th grade. As in the School Service Index, we brought back the calculation to each block to generate a map of the Proficient School Service Index, or PSSI, but to interpret correctly the results, we additionally should consider other variables such as the socioeconomic status distribution in the city or the density of the children population in a given neighborhood. For instance, a good index in a wealthy area is very different from a good index in a poor area. The density of the student helps to determine the magnitude of the problem. since areas with low index and high density of the population are more urgent to address than areas with lower density. We made this calculation for the 22 main cities of Chile, but to be consistent with the previously shown examples, we will only discuss here the result for Santiago. First of all, the density map showed that the children population according to the 2012 census is mainly concentrated in the periphery of the city. Second, these children also are from the lower socioeconomic status. The proficient school service in this map shows a poor coverage on those schools, especially in the periphery of the city, which is also where there are the poorest neighborhoods with more children. The final map shows a spatial cluster analysis. In this analysis, 5 categories of values are identified. Top performance areas with high values surrounded also by high values or high cluster, while the opposite are low values surrounded also by low ones or low clusters. The combination of high and low values, high low and low high clusters are the third and fourth categories, and finally the last area is the one that is not statistically significant. The cluster maps show that in Santiago we have basically two areas: a center-eastern axis, triangle-shaped area of wealthy and well-served blocks, and a ring of poor and bad-served neighborhoods in the periphery of the city, where it's urgent to improve the access to proficient schools. In some areas, clear that it's not a problem of coverage, since there are schools, the blue dot in the map, but they don't fulfill the status of proficiency. The third and last example is a model to predict the student dropout for Santiago. We take into consideration a sample of more than 250,000 students from public funded schools. The machine learning algorithm required to split the dataset in two: a training dataset to calibrate the model and a testing dataset to evaluate the accuracy of the prediction that the algorithms can achieve. We select 127 features from the students, schools, and the blocks where they are located to train a machine learning algorithm. One of the most interesting results was some quantitative features of the school associated to motivation, coexistence, and internal climate of the schools became significant to the model. We implemented and tested 6 models using the Azure Machine Learning Studio, which use a graphical user interface to develop and run models. We tested a traditional logic statistical model and 5 machine learning algorithms: neural networks, decision jungle, decision forest, boosted decision tree, and support vector machine. And the results are the following. The algorithm with the best adjustment was the two-class decision forest with an accuracy of 0.937. The model also provides a relatively low rate of false positive, less than 9%, and false negative, less than 1%. The most important number is the false negative because in the worst scenario, if there is an intervention associated for the student in high risk of dropping out, the false negative case will remain ignored and the false positive will be treated anyway. But it's very hard to policy and decision makers have all this information at hand, structured and organized to be used when it needs. Providing information for short, middle, and long-term decisions should be a systematic task within a government agency such as the Ministry of Education. In first place, the data science technique with the proper visual representation of results are powerful tools to visualize previously invisible phenomena, making them now actionable. In second place, we have tools for visualizing the inequity, allowing to diagnose intrinsic problems of the territories. This makes explicit the need for collaboration between several government bureaus since the challenge and his solution are multidimensional. Visualization tools provide concrete representation to address a problem. In third place, These techniques allow to design solutions based on the size of the problem and not on the size of the territory, since the objective is to minimize the inequity. Finally, with all these methods, we can advance towards a new generation of public policies, a public value intelligence informed by evidence. To achieve that purpose, an online territorial platform we thank to our sponsor for his support and you for your attention. Thank you.